reminder, we have our test on Monday for graphing lines. So wherever I have the orange boxes, that's probably because you have to write something in your notes when I click them. So a system of linear equations is two or more linear functions having the same two variables. So if you have two variables, you need two equations to solve it. Later on in systems, you will eventually get questions with three variables that you don't know. How many equations do you need? Three equations to solve them. If you had five variables that you didn't know, you would need to make five equations in order to solve. Okay, let's just do some guessing and checking though. Can anybody see numbers that make this work? Where you're adding them together, x plus y, and you get 5, and if you subtract them, you get 1. So if x is 3 and y is 2, does it work? So what this means is that if you drew these up, one of them would be a line like this, the other one would be a line like this, and both of them happen to intersect at 3, 2. That's what's happened. The math here was easy enough that guessing and checking gave us an answer right away. Okay? But we're going to learn techniques, because usually guessing and checking will be like, I can't find it, I can't find it, I can't find it, and then you get frustrated. So if you have an algebraic technique that works, that's going to be helpful. So we're going to be doing ones with 2 lines, 2 equations, and 2 variables. We say that the solution of a 2-by-2 system of linear equations, 2-by-2 means 2 variables, 2 equations, represents the coordinates that satisfy both equations. So for example, in the one above, the point 3, 2 makes the first equation work, and it also makes the second equation work. And it is the only point that does that. There's no other point that you add them together and get 5, but then when you subtract, you get 1. So graphically, what did we say? This represents the point of intersection between those 2 lines. So Raylene, you'll have to watch the intro to this. Yeah. And that's the whole unit. Except we have to learn the techniques and stuff. But that is what we're going to be doing and looking at in this unit. So we already figured this out. Is that how you figured it out? Did you look ahead in your notes to figure? Did you cheat? Or did you figure it out? I know, but when you figured it out at the beginning, did you read ahead and cheat? Or did you actually figure it out? Ooh. So this point is the solution, and you can verify it by checking both equations, and it works. No, you couldn't have cheated because it actually didn't show it in your notes. Yeah. Okay, see if you can guess and check to get these 2 to work. You're done? Oh, it's just too easy. Can you guess and check to find ones that work for the first one and ones that work for the second one. Second one's trickier, isn't it?
Not really.
Not, ooh.
Wow.
Wow. Got this unit, eh? Yes, I put all this one that we've been doing. I put all the videos on the YouTube so that we can finish it. And that's my test is on that. Okay. Did you find out that if x was 4 and y was 2? So we write it as a coordinate because this is your x coordinate, this is your y coordinate. So you could, as a coordinate, write it like this. You could also write x is 2, y is 4.
Other way.
And what did you get for the second one again?
X.
Oh, x is, yeah, x is 4. I even said that, and then I went and wrote it opposite.
Yeah.
Man. All right, the next one. What's x? What's y?
3. Y is -4.
3 and -4. So x is 3, y is -4. If you didn't get it, do a double check. Are they right? Nice. Okay. Did your brain find the second one harder? Yes. Okay. First one was easier, second one was hard. So we are going to learn some methods to solve these. Method number 1 is called graph. If you can draw it, and you can draw it nicely, and the graphs match up perfectly at a point, then you can say that's the point where they have the solution. You are going to find that the graphical one is not going to be your favorite one because it takes lots of space and you have to draw graphs, which, because they take space, are a little annoying. But it's good practice from our previous unit because you're going to have to graph all those lines for your test on Monday. So this is good practice. So the solution is the point of intersection between the two lines. Everybody ready if I click to the next slide? Yep, okay. So, x plus y equals 4, 2x minus y equals 8. Give yourselves 3 seconds to see if you can find an answer. All right, time's up. Okay. Ooh, 4 and 0. Nice. Okay, now we're going to see if graphically it works out. So what I'm going to do is I'm going to color code. I'm going to use a green box around the first equation and a blue box around the second equation. Both of those are not easy to graph in this form. Maybe I want to change them to y equals mx plus b. Okay? Or maybe I want to do a table of values. So we remember that when we have relations, we can represent them in all different ways. We can represent them, we've only got the equation. We want to represent it as a graph. So you could do a table of values. You could change it to y equals mx plus b. And you see that you could do that by just subtracting the x on both sides. That would tell me that my green graph has a y-intercept of 4, 1, 2, 3, 4. A slope of -1, which is down 1 over 1, down 1 over 1, down 1 over 1. And so what's really nice about our green graph is I can quickly label all of those points. Draw a line through them all. There's my green line. My blue line. If I get the y by itself, can you see that you could add y to both sides to get the y on this side? Subtract the 8 on both sides. And so y equals mx plus b for the blue line would be y equals 2x minus 8. It would have a y-intercept 2, 4, 6, 8 at minus 8. And a slope of positive 2. So that means I could go up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1. And we have the point where they intersect. And someone in guessing and checking got it within the 3 seconds that it was 4 and 0. Nice. Okay. What's nice about being able to get it with guessing and checking is that you already know what it should be when you graph it. So if you were asked to solve this graphically and you knew that x had to be 4 and y had to be 0, then your graph should show that in the end. Or if you didn't figure it out with guessing and checking, okay, once you found it with graphing, well, you no longer have to guess, but you can still check, right? If I plug in 4 for x and 0 for y, is 4 plus 0 4? Yes. If I plug in 4 for x and 0 for y, is 2 times 4 minus 0? 8. Yes. So it's nice to be able to check things to feel like, all right, I got this right. In fact, mathematically, when you're doing your math, you should be always looking for ways to check. Is this right? Is this close? Is this a good idea? Then you're going to make less mistakes. Or when you do make a mistake, your brain's going to tell you, maybe you should look that up. Something seems a little bit off. Okay. Whew. Second one. 2x minus y equals 10. 2x minus 3y equals 14. All right. You want to do this one together, or do you want to try it on your own? Still a graphing one. Oh, but it says is 3 negative 4 a solution? It's not? How do you know it's not? So we could try it. 2 times 3 minus 4 equals, does it equal 10? Yes, for the first one. The second equation, 2 times 3 minus 3 times negative 4 equals, what does it equal? 6 plus 12? No. Some things about this one. I do want to draw a graph because I think there's some interesting things that come up in this one. First of all, I'm going to color code things again. I'm going to make this one green. Oh yeah. There is some beautiful math that I see happening in this one. And some ugly math. Beautiful math and ugly math. And what we're going to try to do is get away from the ugly math and work with the beautiful math. Okay, the green one, pretty standard. I hope you can see it would be easy to get the green one to be y equals, moving the y to the right side, moving the 10 to the left, 2x minus 10. The green one, straightforward, has a y-intercept minus 10, a slope of 2, which means it's going up from left to right, up 2 over 1, up 2 over 1. There. Those are the nice points that I have. Second equation. I'm going to erase the black for now. If I start rearranging the second equation, can you see that if I subtracted 14 and added 3y to both sides, I would get this? And then if I divided by 3, a little bit not nice, a little bit ugly. Why is it ugly? Because the y-intercept is negative 14 over 3. That is not a nice point to graph. Negative 14 over 3 is, as a decimal, negative 4.66666666. Graph. Not a nice point to graph. And if you tried to graph it, this is the ugly part. Now, we can make this equation beautiful if you can tell me one nice point on the graph. Could you tell me, for example, oh, I think this would be an okay point. If I put in 0 for y, what would x be?
7.
7. Is that not a nice point?
Yeah.
Much nicer than negative 14 over 3. Okay? So if I was graphing the blue one, and I decided to use y equals mx plus b, I would be disappointed because my graph would be hard to do. So even though y equals mx plus b is a nice shortcut for graphing, it is not always the best way to graph. Now I found a nice point. I found 7, 0. 1, 2, 3, 4, 5, 6, 7. 7, 0 is a nice point. I can now find a whole bunch of nice points using my slope. My slope is positive. Does it make sense? Your blue line has to go up from left to right. My slope has a rise over run of 2 over 3. So if I go up 2, I would have to go over 3 in this direction. But I could also go down 2 and back 3, down 2 and back 3. Back. Oh my goodness. This is where I said this has some beautiful maps. Did we have a point where both of them hit? Right there, because that is on my green line. And it's on my blue line. What is the coordinates of that point if I count it? 4 to the right, 2 down, looks like 4, negative 2. Does that work? If I check it. 8 minus a negative 2, yes, is 10. 8 minus 3 times a negative 2 would be 8 plus 6. Yes, it's 14. It works. Okay? And this is what I said in this question. It has some beauty in it, and it has some ugliness. So sometimes, if you decided to graph the blue line with y equals mx plus b, apparently this point right there is negative 4.67. And if you use that point and tried to do everything else, you would run into a whole bunch of problems. And it wouldn't work out nicely for you. But if we found one nice point, then you can use your slope to find a whole bunch of other nice points quickly. And it just so happened to work out that the points intersected. Do you want to know the problem with the graphical method for solving? Is sometimes you are going to get a line like this red line and this black line. And the point where they intersect isn't perfect on any coordinates. And then you're going to be like, I'm stuck and I can't solve it. So method number one, graphically, is only nice when things work out nice. And sometimes they work out nice, but even the equations aren't nice in the process. So this example, I showed you that sometimes we have to find at least one nice point, and then we can use the slope to find other nice points. All right. I want you to try this one on your own. Take 3 to 5 seconds to see if you can guess what works, and then graph them both. If you solve A, try B. Again, take 3 seconds to see if you can figure it out by guessing, and then graph it. If you figure out B, try C. Again, see if you can guess first what works. I'm going to work on all of them in a different order than you're working on them so that you don't copy me. And then I'll show you the answers after. so now I have the answer up for the first one. Probably a lot of you are done the first one already, so you can check. Did your graphs match up at 7, 5? Did you double check it when you were done plugging into each equation to see if it actually did work for both of you? So again, I color-coded things. I first took my green equation and I wrote it in y equals mx plus b so that I knew my y-intercept and my slope. But it was kind of like, oh, the y-intercept went off the graph. But I still was able to work with it. And same thing with the blue equation. Question? So this is what I thought. I wanted to get the y by itself. It's a minus y. So what I did is I said to myself, I moved the y to the right, because that would make it a positive y. And then I minus 2 to the left to move the 2 over to the other side. And I got x minus 2 equals y. And then I just rewrote it with the y equals first. But that's, in my brain, that's what I did to get that by itself. Question? If it says solve by graphing, you do have to graph them. And you do have to show both graphs correctly with the coordinates where they intersect correctly. Right? Guessing and checking is good to be able to say, I know my answer is right, but I still need to know how to graph both of those lines. And I use the technique of changing it to y equals mx plus b to graph. That's not the only way you can graph something, right? You could just do a table of values, or you could find your x-intercepts and y-intercepts. Okay? The nice thing about the slope method is look how many dots I was able to draw quickly. And if I can draw a lot of dots quickly, chances are 2 dots will match up. Well, the graphing ones, they always match up perfectly. So then I know that that's my solution. All right, the second one. Check to see how you did. So I changed them both to y equals mx plus b. I graphed them with a bunch of dots. And I found the one dot that worked for both of them. Yes. So which equation are you working on? Top one or the bottom? So I can move. Again, you're looking at the previous example there, right? So on the blue one, I wanted to get the y by itself. Right now it's a minus y. So I moved it to the right-hand side by adding y to both sides. Then I had a 2 on the right-hand side. I wanted to subtract 2 on both sides. That gets the y all by itself on the right. And on the left, I look, what am I left with? I still have my x, and now I'm subtracting 2. So then the value in front of the x is a 1, which you can think of as 1 over 1, a rise of a 1, a run of 1. So I went up 1 over 1, up 1 over 1, up 1.
I got that one, the other line.
The green one?
Yeah.
Okay.
Oh, we have to do the other equation.
So the green one here, I want to get the y by itself, it's all way plus, I would just subtract x on both sides. Good. All right, I'll put up the second one as people were checking it. How did you do on that second?
on the top equation, are you trying to get y by itself or x by itself?
For part A, I'm using, my method for graphing is using the shortcut from last unit, which is using y equals mx plus b. So if I can make them look like y equals mx plus b, I can have the b as my y-intercept quickly, and then I can use my slope to find a whole bunch of other points quickly.
So it'd be y equals x minus 12?
Y equals negative x plus 12 is the green one.
Oh, you want to know the positive one, great.
Yeah.
How do you do negative x then? Is it just
Negative x is like, so the green equation, it's like having negative 1 over 1 x plus 12. So I still go down 1 over 1, down 1 over 1, but now I'm going downhill because my slope is negative. My slope is still a 1, but now it's negative 1, so that means it's going down 1 over 1, down 1 over 1, or over 1 to the left 1, up 1 over 1 to the left. I guess I could say up 1, back 1, up 1, back.
the y-intercept would be,
Positive 12 is way up there. All right. Want to see the third one? Is everybody ready for the third one? I've gone to the second one a couple times now. Okay, let's go to the third one. Third one, the solution is negative 2, negative 8. Now, some of you, how many, has everyone decided on what math class they're taking next? Okay, now, some of you are going to take pre-calculus all the way through, okay? If you're taking pre-calculus all the way through, then you're planning to finish grade 12 pre-calculus at the end of grade 11, so that you have the option of taking the AP Calculus and Advanced Math course for 2 credits in grade 12. Okay, you get 2 credits, which is nice. It does go the whole year, but unlike grade 9 English, which goes the whole year and you get 1 credit. Okay, so then some of you are like, taking the pre-calculus and might feel like this is a little much for me. Maybe it happens after grade 10, maybe it happens after grade 11. Then you either choose to go into the applied math in grade 11 or the essentials math. And sometimes the grade 10 pre-calculus applied is too hard. You might be deciding to take next semester a grade 10 essentials class instead. Okay? If you are planning on the pre-calculus route and the AP calculus, in grade 12, in the AP calculus, you will be using a graphing calculator. Some of you already have a graphing calculator, I can see. And some of you who are like, well, you might decide next semester, I'd like to buy one. Okay, you can buy one. Sometimes you can find them on Kijiji at less price. If you go to the store, it's going to be, you can buy it from the school, and the school's price is actually cheaper than most stores' prices. So there, you can buy a graphing calculator. So I'm going to show you that on a graphing calculator, you can find this solution as well. And we're going to use this example C, which has the point -2, -8, to see how it works. Now, on a graphing calculator, so you open up your graphing calculator, this is what it would look like when you turn it on. Above the second button in the top left-hand corner is a y equals button.
Is this one where?
That's just a regular scientific calculator. If you're gonna, yeah, or rent. So like here's one that was rented. Once you get to the grade 12. But if you, so turn it on and then push the y equals button and it will look like this. Then what you can do is in the first equation, which is y1, we can write the green one. The green one was y equals 3x minus 2. So I'm going to write in the equation 3x minus 2. The x button is right here beside the alpha button. It has x, a t, a theta, and an n or something. Okay? And then push your arrow down to y2. And in y2, I'm going to write the blue equation, which is -2x minus 12. With the graphing calculator, there is a subtract sign and a negative sign. So when we want to write -2x, we have to push the -2x and then subtract 12. If you hit the subtract sign for the negative sign, it will say error, and you'll be like, what did I do wrong? It's most likely that. Okay? Now, if I hit graph, oops, I'm going to, your graph will most likely look like this to start with. The two lines will draw, and they will cross. And now what we need to do is we need to figure out where they cross. Your window is just set up differently. Hit your zoom button. Hit the zoom button. Go to number 6 for standard window. And then it looks nice. Okay. So now that I have both of them graphed, above the button that says trace, it says CL, it says calc. This lets you calculate a bunch of things. So to get to the blue calc, I have to push my second button and then calculate. And number 5 says intersect. So if I want to calculate where they intersect on my graphing calculator, I can just push enter on that. No, you don't have a graphing calculator. Not this year. You can, if you have one, great, but you don't need it for this semester. If you're like, I know for sure I'm going to make it to AP Calculus, then I would say it's not bad to get one early so you can use it in grade 11 and in grade 12 pre-calculus and get used to using it all the way through. Okay? So now if I push enter on intersect, the question says, what's your first curve? Because sometimes you might have 5 lines drawn and you just want to find the intersect between 2. But it will automatically go on your first one, so you push enter. It'll automatically jump to your second one, so you push enter. And it'll automatically ask you to guess, which you can just push enter again. And it finds it -2 to -8. Now, most of you don't have a graphing calculator already. But most of you have a phone. Some of you are not listening because you're on your phone. That could happen. If you take out your phone, go to the App Store, there is a wonderful app called Desmos. Download that app. What Desmos lets you do is it lets you type in the equations, and what is an advantage with Desmos over the graphing calculator is the graphing calculator you have to write y equals. In Desmos, you can write just about anything. So in the equation that we had 3x minus y equals 2. You can write that directly in Desmos. 3x minus y equals 2, and it automatically graphs it right away. The other equation that we had was, oops, wrong one. There we go. The other equation we had was 2x plus y equals negative 12. So I can write 2x, push enter here, 2x, was it plus y? Equals negative 12. And the nice thing is that you don't need to have a special negative sign. The computer knows when you want to use a negative and when you want to use a positive. So then I write that equation, and you can like scroll in and out. And if you wanted to find the intersection, what would be the intuitive thing to try to do on a phone or on a computer? You'd probably put your finger where the intersection is and say, I'd sure like to click on this point. And you do, and it tells you negative 2, negative 8, just by clicking on it. Very powerful, right? I mean, you can play around. You can now look at like all sorts of crazy equations. I don't know. Maybe you want to play around and woo! That's cool. It's like a pimple. I don't know. So there we go. Play around with equations. And those instructions are there. You can graph all the previous examples, either with Desmos or with your graphing calculator to check. Okay? Of course, on your AP exam, they do not let you use your cell phone. So Desmos doesn't become a possibility. Hence, the graphing calculator is nicer in that situation. But if I was just doing work along the way, I might find Desmos quicker to use, so I might like that. But if I use my graphing calculator, I get quicker at it, so that's good things and bad things with both. We have a homework assignment listed there. We're going to take the last 15 minutes to work on that. I'm also